First of all, I would like to thank Manfred for giving me the opportunity to do this presentation. It was at the last moment, so I had to arrange everything very fast. So my talk is about very technical, by the way. It's not astronomy at all. This is just technical concerning the use of optical fibers. A lot of you have already used these fibers to link the telescope to the spectrograph, and then I will show some applications at the professional level, mainly from the European Southern Observatory instruments, where I used to work together with Carlos and Jesus. Well, first of all, I would like to show a picture about the crowded crowds of people, problems in the observatory. They wanted to observe, and well, this is just a first approach. And well, you know, no, I'm Mexican, and this is my observatory. So this is okay. Well, first, it's not. Okay, just a moment. First of all, no, a moment. Okay, well, anyway, the optical fibers, they are a very long history, and I would like to present here liquid optical fibers. And here there are companies which sell this kind of fountains. I don't know if you have seen them. This is really very, very, very nice. And well, okay, that's all. And yeah, this is just say that the fibers, they are also present in the nature naturally. So there is a stone which is called ulexita, which is made basically by quartz fibers all together, compacted. And what is very interesting is that it's a kind of natural optical fiber. Here we can see the transport of the image from the piece of paper up to the surface, upper surface of the stone. Mm-hmm. Well, the first publication concerning these water fountains dates from 1842 in an article by a Swiss physicist. Well, now, here I would like to show the types of fibers. In fact, there are three main groups of fibers. It's the single mode, multi-mode, and photonics fibers. From the single mode, there are the standard fibers, which are mainly used for telecommunications. And also in this domain, there is the polarization maintaining fibers, which keep the polarization of the light all along the fiber. And also in the multimode group, there are basically step index fiber and gradient index fiber. And in the step index fiber, there are a lot of them. So, you know, there are the plastic and liquid fibers for illumination purposes, silica doped, which I will show you later. They show a better transmission in the UV. Fluoride fibers, which are beyond, the transmission is beyond 2 microns up to 5 microns. There are also the incoherent and imaging bundles. So imaging bundles, they are used in how do you call it? Medical application, but what is the name? I forgot the name. Yeah. Okay. Well, in yes, if you know, for operations, etc. And there are also these tapered fibers where you start with a big fiber diameters, and then gradually they go down to lower diameter in order to simulate a kind of funnel where you simulates a little bit the introduction of a small lens in front of the fiber. And also there are a lot of now non-circular fibers which are square, rectangular, octagonal, even now they call stadiums. It's a kind of circular, truncated on the sides, which potentially they can help for characteristics which I will describe later. And also there are the gradient index fibers, which are mainly used for the telecommunications. And the new type of fibers, photonics, and in astronomy applications, they can quite be useful for doing filtering in the absorption lines, not the emission absorption lines in the close infrared domain for spectrographs working in this range. And there are two types basically, silica cavity fibers where you have a silica core of the fibers, and around you have a number of holes which go along the silica. And these small pores, these small tubes, they act as a kind of cavity which the light goes through. It's like the cladding of a fiber. And then there is also a hollow cavity fiber, which is simply a tube of light. This is like in microwaves, these cables in microwaves. It's important to say that in the Nobel Prize in 1909, Charles CAOS from China and Hong Kong. Okay, sorry, I didn't want to say China, Hong Kong, because sometimes it's a problem. He won the prize for predicting the utility of optical fibers in telecommunications. And what is interesting is that at the same time, Boyle and Smith, they won the Nobel Prize, shared the Nobel Prize from Bell Laboratories for the invention of the CCDs. Now, why to use optical fibers? Well, we all know that they are quite flexible, they are very useful because they are light, and then they offer a number of stabilities, mainly mechanical, because you detach the instrument from the telescope, and then you can put your spectrograph in a thermal enclosure where you can control quite good the temperature and also the atmospheric pressure. Anyway, you see all these advantages, yeah. And I will talk about later about these problems and about the phonometical scrambling and modal noise, and also they are very simple and very cheap. Simplicity doesn't mean that you just put the fiber in front of the star and you transport the light of the star to the spectrograph, because especially at the level of amateur, it's not so easy to achieve this coupling. And then what are the main drawbacks? Here I made a mistake. In the drawbacks is the photometrical stability and modal noise I will talk about. And one of the main problems is the transmission of the fiber, which decrease a lot with the length of the fiber. So here we have examples of the same fiber with the 3 different lengths, 10, 20, and 40 meters. And here we see how the internal transmission of this fiber change along the spectral range. So, and then this is the main drawback for astronomical applications. Because, for example, I will show you later, there are instruments which are in the Coudet room, and they need around 40 meters of fiber from the telescope down to the Coudet room. Then the next big problem is what is called the focal ratio degradation, and this is a kind of entropy problem. So, for example, if you enter the fiber with an input beam, at the output of the fiber, this beam is broadened, is open, is aperture. So, and then why is that? It is because the fiber, as soon as it's bent, the beam started to do additional reflections which increase the angle between the optical axis of the fiber and the exit. Here we have this example where, for example, a parallel beam enters into the fiber, and after some reflections, it goes out, for example, 4. Yeah? And here, for example, here there is another one where it goes the output to f.9, which the entrance f3. So this problem is translated in a loss of coupling efficiency between the fiber and the spectrograph. Here there is an example. For example, if we put directly an F10 beam into the fiber, at the output we will recover here 60% only of the input of the fiber, F10. So it's not at all efficient. And at F6, 80%, and at the numerical aperture, almost all the light. Yeah, not 100% because you have light which goes out all along the fiber. Mm-hmm. So, and here there is plots. There are plots which show practically this problem of focal radius degradation. This is just to show that the fiber behaves better or it preserves better the flux, the energy, if we work at fast beams, F3, for example. And this is exactly what Jack asked me just half an hour ago, is that for good coupling efficiency configuration, it's better to work to inject the beam at a very fast beam and recover at the same aperture. So the losses are less. For example, here, we have here the F output in this axis, and here the total efficiency for different F input beams. For example, if we take an input beam of F8 and we recover the light at F8, we have 70%. But if we inject a beam at F3, we recover 78% of the energy. So that is the reason why it's better to work at big apertures. The problem is that we have to use optics in front of the fiber with a kind of high precision alignment in order to have this coupling. So there are two ways to couple the beam into a fiber, and the first one and the simple one is to use only one lens. And here we have the image of the star, which is at the focal plane of the telescope, and then we put a lens in such a way that the focal plane is at the star, and then it sends beams, parallel beams into the fiber. And here we have the size of the star, which is I would say the seeing, which defines the F number in the inclination of the F number into the fiber. And then here what you can see, because the pupil of the telescope for this lens is at infinity, we are doing the image of the pupil of the telescope exactly in front of the fiber. And when you do the numbers, for example, an F10 beam in a fiber of 100 microns, you can see that the focal length of this lens is of 1 millimeter. 1 millimeter. So it's not easy to find lenses of 1 millimeter. Okay. And then the other coupling method is to project directly the image of the star in front of the fiber with a couple of lenses. Yeah, and then something that I forgot to tell you here is that for a fiber, the model concerning the pupil of the fiber as an optical device is at infinity. So in order to reduce the focal radio degradation, we have to inject the beams into the fiber in such a way that the pupil is at infinity, or what is called the telecentric injection. Here is the same. We have same in the sense to inject with telecentric beams. So we have here telecentric beams because the pupil it's almost at infinity. It's M1 in most of the telescopes, and the image of the pupil of the telescope by this entrance lens is here, which is placed at the focal plane of the second lens in such a way that the pupil seen by the fiber is at infinity. And then this is the best coupling in order to reduce the focal ratio degradation. At the output of the fiber, we need to reconvert the F3 beam, or the beam you consider the best for compromise concerning you will see resolution and flux, is to use a lens here which converts in this case, the specific case, F3 beam into the F number of the collimator of your spectrograph. So this here I put a lens, but it's not a single lens. It can be a couple of lenses, as in the first case, or a single lens with is glued directly here. And concerning the lenses, what we use is what is called rod lenses, where it's a plano convex lens, where the focal plane of the lens is on the rear surface of the lens. So the lens is made in such a way that the focal plane is exactly on the entrance or the output of the lens, where we glue the fiber into this surface in order to reduce the reflection losses by Fresnel losses, you know, of the fiber and the lens. Here in the laboratory, together with Carlos and Jesus, we prepare fibers with is called green lenses. Green lenses is gradient index refraction lenses, where you know they are circular cylinders where the refraction index in a radial way change the refraction index in a kind of parabolic shape. So you have a high refraction index in the middle, in the center of the fiber, the lens, sorry, and it goes down with a lower refraction index in the at the edge, and this way the fiber, the lens acts like a kind of small lens where the focal length equivalent for this lens can be really very small. Here, the advantage of these green lenses is that they are very cheap in the sense that they cost around 30-40 euros. Yeah, instead of the plano, the road lens. The road lens, they are, because they make them one by one, and they are very expensive. But here, for example, it's around 30-40 euros. The problem is that the company who sells these lenses, Green Tech in Germany, the minimum quantity is 10. So at the end, you have to buy 10 lenses for 400 euros. But it's worth to do it because in the laboratory, the size of this fiber, for example, is 1 millimeter, and this is 2 millimeters long. You know, so believe me, it's not easy. It's not easy to put inside. So sometimes, for any reason, you how you say it goes out, yeah, and then impossible to find the lens. You cannot find a lens. That's why 10 is good. Okay, and here we have two examples. Here one on the single lens, and then here we have two lenses which simulate these two lenses where you put the image of the start at the entrance, and then the image of the start at the entrance of the fiber. That is the ferrule of a standard connector. Well, now how do we this? I don't want to spend too much time because you know that there are a lot of ways to be sure that the image of the start will enter into the fiber. Here we have the most common way to do it is to image the telescope at the pinhole mirror, where the light is reflected to a lens and then a camera or directed the eye, and behind we have the micro lens and the fiber. So that is the easiest way to do it. And here, for example, we have we develop this kind of idea on a practical example. So here comes you know, I don't want to spend too much time in this one. And here, this is just to show how it looks like when you look at with a camera the star just in front of the pinhole. This image is just to say corresponds to HARPS. Is this high resolution spectrograph in La Silla, which is dedicated at that time for research of exoplanets. And here you have more ways to do. Just I go very fast. Even you can use beam splitters it depends of the possibility or the ideas you can have for do this coupling. But what is interesting is, for example, this way to couple. This one is here. on a single glass plate, you glue a fiber from behind, you know. It's very simple. It's very difficult to do it because how you glue a fiber there and then it stays there. But it's just to say that this idea, it was patented. So this is really, and then another way which is very, and then the equivalent, you can do that with a thin support to avoid vignetting of the support when you are looking the image of the star in front of the fiber with a camera or the eye. And one idea also which is very useful, is quite used in professional fiber bundles, is this coherent fiber bundle, where the fiber you wanted to use as a channel is in the middle and surrounded by a number of fibers, which at the output, you keep this, you decouple the fiber in the middle, of course, but you keep the geometry of the other fibers. Here, for example, we have an example in the instrument which is called FLAMES at the VLT, at the 8 meters telescope in Paranal, and they use this principle for using a guiding star in front of a multi-object spectroscopy, where you use 140 fibers for putting each fiber in front of the star. And then this is the way they use for be sure that the pattern of stars you are projecting on the focal plane of the telescope coincides with the number of fibers which are behind, in order to be sure that each fiber is in front of the star. Sorry for the bad quality, but it is interesting to say that LOD is an spectrograph which was used by Michel Mayor and Didier Queloz from Geneva Observatory in the OHP, the Observatory of Haute-Provence in France. And that is the instrument they use, this spectrograph, which is here with the optical fiber, which, well, you cannot say, but it is here. And this is the 1.2 meter telescope. And with this telescope and instrument, they discover the first exoplanet in Pegasus 51. Okay. Sorry. And here we have the way how HARPS is coupled with the optical fiber at the 3.6 meter telescope in La Silla. And for that, this is the optical path of the fiber. And as I told you, we need 40 meters of fiber. And you see that these 40 meters, in the very blue, the efficiency is no more than 50%. Well, here you have the coupling of the fibers at the Cassegrain focus of the 3.6 meter telescope. The fibers are here, and they go there. And here, what is interesting to show is the coupling of to one of the molds of the fiber. And here we have a small lens, but what is, no, the lens are here, sorry, one or two, but between the lens and the pinhole, there is the shutter, because there, in HARPS, in these spectrographs, which are dedicated for high accuracy measurement of the radial velocity, there should be, or there must not be at all any mechanical function inside the spectrograph, because it can heat up the instrument, etc. So the shutter has to be outside, and then we put the shutter just there, and it was really a very nice challenge. And the guys in Chile, the Chileans, they could do it. And here this is the piece with a motor. Here this is the pinhole, and behind is this small shutter. Well, here you have the spectrograph harps, and you can see here the size of the shell, which I don't remember what was the size, but this is something like 50 centimeters long. Okay. Well, now I put another example. It's espresso at the VLT, where one of the modes of observation is to use simultaneously the 4 telescopes. So here you can see the 4 telescopes are pointing to the same star, and the light is sent to what is called the Couder room in the middle of the 4 telescopes. And with this configuration, finally, after around 25 years, ISO could put the 4 telescopes simultaneously in such a way that the equivalent telescope is a 16-meter telescope. Mm-hmm. And here I wanted to show you, it's not the right place, but this is an optical system to reduce the photometrical variations of the fiber. I will explain later what is this problem. And just to show you the optics which are needed. Here there are 2 doublets, which are 3 millimeter diameter and 7 millimeters long, so 2 doublets, one here, and they exchange the pupil and the image of the fiber. I will explain you later. This is just to tell you that for harps, this is the configuration, and this one is for espresso. So as you can see, it's really much more complicated what we do in amateur way. No? Well, here I wanted to show you espresso, the size. This is the mechanical support going inside the vacuum chamber. Here you see the 2 covers, and here what is interesting in this picture, it's the shell. The shell, which is 1.2 meter long, you know, and it is by 30 centimeters wide, and is composed by 3 individual shells. And they use in Milton Roy Richardson, it was like a, how do you call tampon, no? This pack, no? Stamp, yes. So the master, it was 40 centimeters by 30, and they had to put on a single piece of glass here. They put the glue, and then extremely precise. They put the 3 the samples, and the main problem at that time it was to keep the parallelism of the groups in the 3 modules, because otherwise, if this is what Manfred had this problem with the spectra, if there is a small angle, the spectrum change the dispersion is inclined, so you have 3 dispersions. Here you have the detector. This is the detector was used in espresso, and I wanted to show you a small video how the light is going from the telescope up to the detector in espresso. Here we have the CUDE path of the VLT, which is composed by a prism, and then from there they go to the CUDE room, which is around 40 meters from each telescope to this room. Here we have what is called the front-end unit, where we have the atmospheric dispersion corrector, and here we have optics for the stabilization of the pupil and the star in front of the fiber. Here we have the calibration fibers for illumination of the science fibers. And here we have a turning system in order to send the beam from one of the telescope or two telescope or three or four into the fibers. And then here comes the spectrograph, and here this is the spectrograph, which works with the principle of wide pupil, and there is also a pupil slicing of the system. So as you can see here, this is the fibers. This is again the structure. Here you see how it was entered to inside the vacuum vessel, and here there are mainly two rooms for thermal stabilization. Okay, so this is and now there are at present projects which use multiple fibers. As I told you, in HARPS, or for us, for amateurs, we use one single fiber to put the light of the star in front of the fiber for only one fiber. But long time ago, there were instruments which would use a number of fibers to simultaneously record a spectra of, at that time, in 30 years ago, with the first multi-object instruments, to record the light of galaxies in a cluster. Here in moons is a project which is almost finished. It will be installed at the end of the year at the VLT, in one of the VLT telescopes, and they use 1,000 fibers. Yeah, and the way to put the star, sorry, the fiber in front of the star, it's with this system, which they have two rotation axes. That is the arm. The fiber is here together with the lens. The lens is here, and it can rotate. And then there is a second rotation to provide the a map of in a small portion of the fiber in front of a portion of the sky. And here you see the integration of each module here in this structure to hold all the positioners. And this answers the question of Joan, is that this instrument splits the light in 3 domains, going from 380 nanometers in three parts, and here we can see each part, and then they use as a dispersion system is what is called the volume phase holographic gratings. And here you see the cameras. There is another project which is called Foremost, and also they will use 2,436 fibers, yeah, and they will install also at the beginning of the next year in the Vista telescope in Paraná. And there are two spectrographs, one for low resolution and a second one for high resolution. High resolution, it's not like Espresso, which Espresso had three modes of observation with the three resolving power. It's 60,000, 120, and 220,000 resolving power. But because of the aberrations, the effective resolving power is 190, 180,000 resolving power for Espresso. And here, the high resolution is 40,000. But anyway, it's not negligible. There is an instrument which is called UVES, which was the first high-resolution spectrograph in Paraná, and it works at 40,000 resolving power. Here you see the way the fibers are in front of the focal plane of the telescope. They are needles in a configuration that the Australians, because it was made in collaboration with Australia and Durham in UK, it's what they call echidna system. You know the echidna, no? With the each needle down, it has two magnetic kind of magnetic motor, which makes the fiber in a certain range, spatial range portion on the sky. Now, I wanted to show the principle of the image slicer. Is you know, as some of you know, it's an artifact to increase the resolving power of the instrument with keeping a high throughput. Here we made this image slicer with two mirrors. These mirrors are made of cover objects in microscopy, which are 140 microns around the thickness. Yeah, and with that we could make this arrange where the light, when see here the light coming from the telescope, goes, okay, in our case it's optical fiber, comes here, half of the half moon of the image of the fiber goes directly into the spectrograph, and the other half is reflected and displaced by this second mirror with a certain angle, and the result is that here for Fletcher's spectrograph in Jena, we use octagonal fiber, and this is the final result. And here is the orders of thorium argon, and here you see the two slices. And then you see that with this device we double the spectral resolution. Yeah, and the efficiency is quite good. The efficiency of the first slide is 1 because it goes directly to the spectrograph, and the other we have in this case we use aluminum, and the efficiency is a little bit lower. It's already around 80%, but still it's not so bad. And with this artifact, we could increase the resolving power of flechas. Well, I think this is, no, sorry. I wanted to talk about the problems with the fiber, which is the photometrical stability. When here we have, this is the entrance of a fiber, and then this is the star put in the middle of the core of the fiber. But because of guiding problems, the problem is that the star is not stable exactly in the same place, but there is a small displacement all along the observation. The fiber is not a perfect scrambler, and in this example, which we made at ISO, we illuminate a fiber with a small spot, which was smaller than the diameter of the fiber. Here we see the image of the fiber output with a microscope, and when the spot is in the middle, we have a very uniform illumination of the output of the fiber, but when the spot is on the side, we see an asymmetry of illumination. And then what is the problem with this one is that the point spread function or a single line, for example, emission line or a calibration line, the center of mass is a bit shifted by this memory effect. So, and then this reduces or limits the capacity for good measurement of the radial velocities of the instrument. And practically, this shift has to be around 1,000 the size of the fiber. So in our case, it has to be much less than a few, 1 micron or even less. But this is when the star goes from the center to the edge of the fiber. But the guiding system is not so bad. So it keeps the star with a tenth of the size of the fiber. So here at the end, this distance of the point spread function is much smaller, is the order of nanometers. There is another problem, is what is called the modal noise. There is two effects when you use a laser, for example. When you use a laser and you inject into the fiber, you have two patterns. If you spread the laser on with a lens on a sheet of paper, what you see this granulation, which is called speckles. Okay, they are made mainly by problems in the cavity of the laser, as you know. Yeah, but with the fibers, here we have a fiber which is on the first one is a 10 microns core diameter fiber, and we inject. It's not written here, but we inject a laser, helium argon laser, red one, and by properties of these single mode fibers, you have a few modes. In this case, here you have around three modes. This structure is interference in the camera, etc. But this one is, you see that there are three transmission of three modes transmitted along the fiber. But if you move a bit the fiber, yeah, these three guys, they move all around. Here we have a 25 microns fiber where we have around 10 modes, and when we illuminate a much bigger fiber, the number of modes grows as a square of the diameter of the fiber. In this case, we have really thousands of modes. And it is not a speckle. The speckle, they are still smaller. The speckle, in fact, they are inside here. And in order to scramble all these problems, because as I told you, when you move the fiber, these modes, they move and then they make this modal noise, especially when you calibrate your spectrograph, because in HARPS and espresso, the calibration lamp is not anymore a thorium one, but is the comb system, which is this system which have thousands of individual lasers, you know, which are extremely well stable. This is really the top of the calibration. So, and each spectral line of this comb system is an individual laser, which is extremely sensitive to this problem of modal noise. And here there is another problem which appears with in illumination of incoherent light. The previous one was coherent light, and here for some cases, especially probably you detect that, and also in professional spectrographs, when the diameter of the fiber is small, around 50 microns, these modes, they make a kind of noise in the spectrum. Here you can see that on the continuum of the spectrum, yeah, it's a flat field. It's a flat field. You see this kind of noise, in addition to the Poisson noise, the normal noise of the light or the electrons into the detector, which they are the square root of the number of electrons in the pixels of the CCD. And this noise, it's attenuated if you scramble, you agitate the fiber with a vibration system, okay? And the same problem, and it's even worse in the low-level light. Here, we were discussing that with Joan, which had this big problem. You see, when you move a bit the fiber, this pattern changes, so it makes really a lot of noise. And then when you do agitation of the fiber, you average this noise, and it's highly reduced. And one of the reasons why appears that is because in some spectrograph, the image of the fiber is projected on a physical slit with a variable width. And when you do that, here the number of modes, you are cutting them in such a way that you select a few number of modes, and then this modal noise is increased because you have few modes. This is one of the reasons. But other one is directly from the structure of the fiber, which was prepared when you put the fiber into connectors, etc. Here, this is the system we use for HARPS and for espresso. Is a kind of disc where we put the fiber, and this disc is coupled with a electrical motor with an eccentrical mass in the axis. So when it started to turn, this disc is suspended by springs. So when the motor turns, it vibrates the the fiber. And here you can see with a laser. Here it's illuminated with a laser. It's the same example I put before. You see the thousand of modes, and here you see on a profile this mode how they are. And when you put the system in operation, you smooth this this noise. This one is kind of Newton rings by the window of the CCD. Now, what is sorry? What is interesting is for measurements, high precision measurements of the radial velocities. The spectrograph is in vacuum and with temperature control. What is interesting is, for example, if you have an error measurement of 1 meter per second, yeah, it represents a shift of the spectrum of 10 to the minus 5 angstrom on the CCD, which is 15 nanometers or 1,000 of 10 microns pixel. Yeah, so this is really very, very, very small. And also, when you have this error of 1 meter per second, you have to control your spectrograph better than 100 of Kelvin, okay? And also by pressure, which changes the refraction index of the air into the spectrograph, it has to be better than 100 of millibar. Yeah, that's why we use vacuum vessel, and we control the temperature to 1,000 of Kelvin. It doesn't mean that it's absolute, because there is a confusion. They say that it's impossible to control 1,000 of a degree. Not absolute, because the people, when you say temperature, the temperature in Paranal is 16 degrees in the Couder room. And then it's impossible to have 16.111. No, it is just the relative. The detector can even be better. This is a problem of accuracy and precision. Here we are talking about precision, not accuracy, which is absolute. Precision is like, you know, no? You have a meter, which in reality is 90 centimeters, but it has 1,000 of 10 of less than millimeter, no? It's very precise, but it's not accurate. While if you have a real meter, but the lines is 1 centimeter, is extremely accurate, but not precise. You see this difference, and this, because there was a big discussion about this problem of temperature. Well, no, sorry, yeah, this is, that's all. I wanted just to show that for amateur purposes, the fibers which are used in telecommunications, which I say gradient index fiber, they can be used also for amateur purposes because they are extremely cheap. So extremely cheap, yeah, no, 10 euros, 5-10 meters. But the transmission is as you can see here, is quite good. So it's just to say that you can use that. No, so it's just to say how is calculated the transmission for different lengths. Okay, thank you very much for your attention. No question? Yeah.
back if you can you go back a few slides to the 1000 precision? No. Go farther. It was one of the latest that you were. It's at the end. It's almost you are going to the beginning.
Yes.
No, go to the end.
No, the end is.
Okay.
Oh, I mean, too much. Wait.
You were talking about the precision, and then you mentioned 1,000 of an angstrom, and then you say equivalent to 15 nanometers. How do you get to this value of 15 nanometers?
No.
What is the meaning?
It's a theoretical. It's. Yeah. Here. Yeah. No. You know that the radial velocity is a shift of the spectrum.
Yes.
Okay. In radial velocity, if you put 1 meter per second shift, it corresponds to 15 nanometers. And it means 15 nanometers is already a few atoms in the silicon of the CCD. You know, it's really very, very small.
Not the wavelength, it's wavelength.
It is not wavelength.
No, it's not wavelength. This is just to say that the shift of the spectrum moves by 15 nanometers on the CCD. If you wanted to have this precision, you have to detect this shift. And of course, the way they do it is by, it was mentioned by, I don't remember, by correlation, by convolution between a pattern of 1,000 of lines with respect to the spectrum of the star you are observing. And the precision increased by the square root of the number of the lines that you are using. That's why for the G stars, like the sun, it's quite easy, quite precise to use this method because you have a lot of lines. You know? It's less for B stars or blue stars. Yeah, okay. But this is the point. This is just an example that you have to be able, in order to have, because the accuracy of harps and espresso is of the order, harps is around 1 meter per second, and espresso is 30 centimeters per second. So it means that if you glue a thorium lamp in your back, and then you started to run, espresso is able to say, you are running at 2-3 meters per second. So this is just to say that this is really extremely precise. But you have to be able to detect movements of 1 of 1,000 of a pixel. Mm-hmm. Okay. Yes, Munter.
Yes, another problem for us amateurs. How do I mount the lens in front of the fiber?
I must say that yes, it's difficult, but there is you can avoid that. You can avoid because you don't need always a micro lens. It is true. When I put the pictures of these lenses in front, you need a very precise micrometer, the order of microns, in order to, what we do with Carlos is to use a piece of paper glued to this positioner, and in the middle we have a hole, a square hole, where we put the lens, and then very precise, because it has to be put the lens the order of 1 or 2 microns with respect to the fiber. Otherwise, the beam is closed. So it's not easy, but let me see. Yeah, here. If you use this technique, for example, this one, you don't need a lens because here you are, for example, you have a f6.5 telescope, okay? And if you use a focal reducer, you inject at f3. And then you don't need any lens. Directly you put, but the problem is to put the fiber in front of the pinhole. That is not easy. What we do, it's we have the fiber glued in the connector, and we polish with this angle the ferrule until reach the fiber, and then we approach the connector at this level. Yeah. So for some applications you don't need, provided that the image quality of this focal reducer is a good. The focal reducer is Barlow. I think it's the Barlow lens. No, what is the Yes, exactly. Mm-hmm. Okay. Mm-hmm. So you don't need it in this case. Mm-hmm. And also another one is this one. This one is this or this one. You know, you don't need a very small lens. The problem with these two examples is that you need a mechanics which has to be extremely stable, and at the end you have to do a very precise projection. You illuminate your fiber from behind, yeah, and you, with a microscope in front, you move the set, the ensemble of these two lenses, X, Y, until you put and see the focus until the image of the fiber is just in front of the hole. But it's possible, yeah. Mm-hmm. No, but frankly speaking, in this case, I think we can help you if you have this one to make this kind of fiber. Of course, we need some. We cannot provide the material, etc. So, and also we have to charge because we are collaborating, not collaborating, but I would say with Bader Planetarium. We have a laboratory there, and and then we can do some virus, but with a charge, because Bader will say no, you don't work gratis. But what is also another point. It's just not because shellac is want to criticize, but if you measure the efficiency of the shellac fiber, we did an estimation according to some astronomers which provide some numbers. It's around 50%. While if you use a lens in front, well aligned, etc., we can reach 70, even 75% of total efficiency, which is not so bad. Mm-hmm. Yeah, thank you. Mm-hmm. Yeah.